Hello. So today we are going to start a new chapter, chapter 11 about covariance and correlation. So this is so far we learned some important statistical inference methods, estimator like confidence interval and hypothesis testing. And now we are going to change the gear and we will go back to chapter 3 and 4 about numerical description of random variables. Let's review what we have done in chapter 3 and 4. In chapter 3, we learned measures of location or measures of central tendency. And in that chapter, we learned the mean and the median. So basically, the measures of location capture the representative value, right? The center of the distribution. And then in chapter 4, we learned measures of variability or dispersion, spread, inequality. Like for example, variance, standard deviation, range, interquartile range. So those capture dispersion, right? How variable the random variable is or how spread out the distribution looks. And these two chapters, so far, including those two chapters, all the inference methods assume that there is only one random variable. So confidence interval, hypothesis testing, and the sampling distribution, normal distribution, binomial distribution, all of the theory was based on a single random variable. But often we are very much interested in the relationship between some variables, more than one variable. So in chapter 2, we learned one method to capture the relationship. That was the conditional probability. So conditional probability is a way to compare different groups or relationship between them. For example, statistical independence, we learned in chapter 2, means that one variable has no effect on the other variable, right? So, and we are going to learn more commonly used, more important numerical measures to describe the relationship between two variables in this chapter and the next one. In this chapter, we learn the covariance and the correlation coefficient. Simply, I may call it correlation, but a more official, more formal name is correlation coefficient. And in the next chapter, we are going to learn the regression model. Regression model is the workhorse model in almost like say 90% of research in economics is based on the regression model, some kind of regression model. There are a lot of variations, variants from the regression model, but we are going to start the most basic and simplest possible regression model. And then if you are interested in more about data analysis in economics, I recommend you to take 420 applied econometrics. Maybe we'll start from that course. We'll start from the basic regression model. Okay, and then Keller, in the Keller textbook, the related chapters are this, and simply just look up covariance or correlation coefficient from the index. Then you can find related chapters. So let's think about an example. Let me start with an example about climate and economy. So, this is a real data. It's a real data, and suppose that there is a data set of 183 countries, and it contains two variables. One is average yearly temperature between like 30 years in Celsius. And the other variable is GDP per capita in US dollars, in like standardized to 2005 US dollars. And the real data can be found here, Lebanese Economy Forum. I don't know what it is, but so it's interesting that if I order the countries in the order of GDP per capita, Qatar is at the top, Luxembourg is the second, Macau, Singapore, Kuwait. So what we are going to do here is, I don't know if it may be a stupid question, but let's just study the relationship between temperature and GDP per capita. So if temperature is high, then would GDP per capita be higher or lower? They may be irrelevant, but just as an example, let's think about that. So the first thing we can do is to make a scatter plot. So when you have one variable, visualization is usually by making a histogram. Histogram is just for one variable, and it shows how many data are in each, how many observations are in each interval. If you make a lot of intervals and then make a bar on the interval, that represents how many observations each interval has. But scatter plot is for two variables. Now it's for two variables. Say in this example, temperature is on the horizontal axis and GDP per capita is on the vertical axis. And one point, one dot represents one country. For example, Qatar is here because Qatar's average temperature is above 27 degrees in Celsius, and GDP per capita is nearly $80,000. So Qatar is located here. And Canada and Russia are like far left because their average temperature is below zero, below freezing point. So they are here, and their GDP per capita is their vertical axis. And like that, Norway, USA, Singapore, Macau, Luxembourg, and all the countries are on this plane. So, and as you can see, because the data had 183 countries, this scatter plot had 183 dots. So one dot is one country, and their location is determined by their values for these two variables. So from this scatter plot, it shows the relationship between those two variables, but it's unclear. From this picture, it's uncertain what's going on. So let's simplify our question. What we want to do is we want to draw a trend line. We want to draw a straight line going through the dots, and then our questions are like, what is the direction of the line? What is the direction of the line? So is it downward sloping or upward sloping? So depending on the slope, you may say that colder countries have higher GDP per capita or lower GDP per capita. So it will show the tendency, direction of the tendency. And second, how strong is the relationship? The strength is when you draw a line, trend, then how much deviation each country had overall plot has. So here, like say Luxembourg is very far from the trend. So Qatar is also very far. So from this picture, you can tell the relationship is not that strong. Anyhow, like this is a simple summary of what we are going to do. We are going to make a line, straight line, and we will tell the slope, and we will tell the dispersion, deviation from the trend. And these two will be our main interest. So before starting the main analysis, I would like to emphasize that our analysis we study in this chapter can be limited. It's limited to linear relationship. I said I'm going to draw a trend line as a straight line, but sometimes the line may not be straight. So the trend may not be straight. For example, in this graph, if you see this kind of graph, it's a beautiful graph that perfectly fits into a straight line. So even though there is small deviation, but overall the fit is clear. And so there is a straight line trend going through all the observations. It clearly has a linear relationship, linear trend. However, in this case, if you look at this panel, the pattern is going down here and then up. It's like V or U-shaped relationship. It's nonlinear. Slope changes here and there. So this example, this kind of example does not fit into our framework. Later, if you learn more course, if you take more courses, and if you study more in a graduate program, there are techniques that handle this nonlinear relationship. But in this course, we are not going to extend our framework because that will be more difficult. So to keep everything simple, I'm going to assume linear. And also, this is another example where the slope changes. Flat, then going up. So like flat going up and like going down and up, or whatever. If you see nonlinear trend, if you see a clear nonlinear trend, it can be a problem. Or what happens here is, if you use our framework to this kind of data, if you make a straight line going through the observations, you are going to have a horizontal line. A horizontal line is the average slope. So then it looks like it's flat, but actually it's not flat. Or if you use a straight line to draw a trend line here, then your line will be like this, which is more flat than the actual slope here. So actual slope is like this, but your trend line will be average of some kind of average of them. So in those two cases, linear relationship may not capture what you want, the underlying relationship. So in this case, you have to understand what's the limitation of what you're doing, and I recommend you to have a look at the scatter plot if there is any nonlinearity underlying the data. So and then I'll show you more plots. This is an example of the direction of the relationship. So if you see this kind of downward sloping, say clearly downward sloping, then this means that as x increases, so this is x, horizontal axis is x increases, y decreases as you go to the right, then the trend is going down. And on the other hand, to the right figure, as you go to the right, it goes up, trend goes up. So this is an upward sloping. So we call this positive relationship. When it increases, when the horizontal axis increases, vertical axis also increases. But this case is negative. It increases, but then vertical axis variable decreases. And in the middle is like zero, nearly no linear relationship. If you make a trend line, it will be flat, horizontally flat, or you may make a perfectly vertical line. Either vertical or horizontal line imply no relationship, zero, neither positive, neither nor negative. So this is an example of no relationship, but it's positive, it's negative. And this shows the strength. So this pattern is much more strong. It shows much stronger relationship between those two variables. If you make a trend line, the distribution is much more tighter, closer to the trend. So the deviations are smaller overall. On the other hand, this kind of graph shows bigger deviations. It's more errors from the trend. So the differences between the actual observations and the trend has bigger differences. So the relationship is weaker here. So these are the basic like a way of analysis, even though it's just simple eyeballing, but basic concepts of what we're going to do later. So in the next video, we are going to quantify. So far, we just talk and like goes up, goes down, and strong, weak, but that is not clear enough, rigorous enough. So we are going to quantify this kind of analysis in the next video. Okay, so see you there. Bye.